Hello everyone, I'm Johanna Schröder. I'm a PhD student in the group of Professor Ahrens at the University of Bern in Switzerland. Today I will talk about my recent publication about the gas diffusion electrode setup for testing catalysts of electrolyzers. Electrolyzer catalysts are normally tested in rotating disk electrode setups in fundamental research or as comparable to the real device, the PEM electrolyzer in membrane electrode assemblies. The use of both setups, however, includes some challenging aspects. For example, it's challenging to go to high temperatures in the rotating disk electrode, and as compared to the real device, only thin catalyst films and aqueous electrolyte are used. On the other hand, the setting up of a membrane electrode assembly is time-consuming, and also, for example, for catalyst film preparation, special equipment is needed. In addition, Bern et al. Recently presented in stability tests performance contradiction between RDE measurements as compared to MEA testing. Therefore, a device would be desired that combines the advantages of fast testing in the RDE setup with the real conditions in the PEM electrolyzer. In the fuel cell community, recently gas diffusion electrode setups were presented as new testing device, as there is reduced mass transport limitations found as compared to rotating disk electrodes. In the gas diffusion electrode setup I'm using, humidified gas is introduced into the cell, passing the carbon dust gas diffusion layer and reaching the catalyst layer. The catalyst is separated from the electrolyte with a proton conductive membrane. I was so far using the gas diffusion electrode setup to perform accelerated stress tests in acidic media. In addition, we can combine the gas diffusion electrode setup with different analysis techniques, as for example small angle X-ray scattering. After testing fuel cell catalysts in the gas diffusion electrode setup, the question was if it's also possible to test that catalyst for the oxygen evolution reaction in the gas diffusion electrode setup. In the study I want to talk about today, I was using iridium oxide black as benchmark catalyst from Alpha ISE, as it's accessible by everyone and used in many studies. To test this catalyst, I was performing different current density steps and measured the corresponding potential. Today I will talk about 4 aspects of my work. First, I will talk about the influence of the gas flow rate and why we need to consider this in our way of measuring. The second point, I will compare results obtained in the gas diffusion electrode setup with measurements in RDE electrode setups, the standard testing device for catalysts. At the third point, I will talk about the stability of the carbon-based gas diffusion layer that we are using for testing. And the last point, I will compare the performance result obtained with this carbon gas diffusion layer with the titanium felt that is regularly used for electrolyzers. I will start to talk about the influence of the gas flow rate. And the reason why that matters is that we are introducing the water that we need for the oxygen evolution reaction by humidified gas. And one can imagine that depending on the gas flow rate, the gas might be differently humidified. As a consequence, it could be that the amount of water that is transported to the catalyst is differing, and therefore mass transport limitations could be as expected. Applying different flow rates between 10 and 190 milliliter per minute, and the results are showing that between 40 and 190 milliliter per minute comparable results in activity are obtained, and only at the low flow rate 10 milliliter per minute we see some deviation. Looking now at the tafel plot, we see that above 40 milliliter per minute the same parallel tafel slopes are obtained, and only some nonlinear behavior is seen for very low flow rates. So the conclusion is, as long as we stay high enough, in this case 40 milliliter of minute, we reach comparable activity results in the gas diffusion electrode setup and don't expect any influence of the flow rate. The next aspect is a comparison of measurements in the gas diffusion electrode setup to the rotating disc electrode setup, the standard testing device. The RDE measurements were performed by my colleague Vlad Mins. First, we will look at results obtained at 30 degree in both setups. In comparing galvanostatic measurements in the GDE setup to measurements in potentiostatic mode in the RDE setup, we reach really comparable results. However, at 60 degree, the results obtained in the RDE setup seem to be more active, but we also see quite huge deviation in the current density. The differences between the activity obtained in the RDE as compared to the GDE setup at 60 degree might be traced back to an instability of the rhodium oxide at 60 degree in the RDE setup. Performing cyclic voltammetry in the RDE setup, we can see that at 30 degree a stable activity is reached, while at 60 degree and deactivation of the catalyst is seen. As a conclusion, we can say at 30 degree we reach comparable results between both setups, while the gas diffusion electrode setup even enables measurements at high temperature close to electrolyzer temperatures. As next aspect, I want to talk about the carbon-based gas diffusion layer that I'm mostly using as substrate. When we look at an SEM cross-section, we see a carbon fiber structure and on top a porous carbon layer. Carbon is showing limitations at high current densities, and for our activity testing we need to show that there is no interference with the possible degradation during our measurements. Therefore, I was applying a current density of 10 mA per milligram iridium for an hour. When we look at the results obtained at 60 degree, we see really a stable performance for all three repeats. Only for repeat 2 there might be some degrading of the carbon. But in total, due to the stable performance, we can say that the carbon substrate is stable enough not to interact with our activity measurements in the GDE setup. As last aspect, I want to compare the carbon gas diffusion layer that we are normally using for gas diffusion electrode setups and compare the activity to measurements with a titanium felt that is regularly used in electrolyzers. And something I was not talking about so far is the film preparation. And this is at this point necessary, as I had to look into it to enable the preparation of catalyst films with a titanium felt with regular lab equipment. The deposition of the catalyst layer on top of the carbon-based gas diffusion layer is done by vacuum filtration. Therefore, a catalyst ink is introduced into a funnel, and by starting the vacuum, the catalyst film is deposited on top of the GDL. A colleague of mine, Etienne Berner, was looking at SEM cross sections and performing EDS mapping. We could see that the iridium oxide is really deposited only on top of the porous carbon layer, and therefore we can say that with the vacuum filtration we found a straightforward way to perform homogeneous catalyst films on top of a carbon-based gas diffusion layer. On the other hand, for the titanium felt, the vacuum filtration was due to the high porosity of the titanium felt not possible. Therefore, I was increasing the viscosity of the ink, not using isopropyl water anymore as for the carbon gas diffusion layer, but instead a glycol-based ink. and it was possible to deposit a drop on top, but during drying overnight we still saw some permeation into the titanium felt. Therefore, we took a closer look in the comparison of both substrate. And this porous structure we see in the titanium felt is also found in this fiber structure of the GDL. But this porous carbon layer contains some Teflon, and therefore the hydrophobicity is increased. Therefore, also for the titanium felt, I was spraying for some Teflon on top before drop casting the glycol-based ink, and as a consequence it was possible to decrease the permeation and obtain a catalyst film deposited on top of the titanium felt. Another aspect I was not talking about so far is the preparation of the working electrodes. And at this point now I want to talk about the preparation we are regularly using for the gas diffusion electrodes in our group, and I will compare what is necessary for the preparation of the titanium felt to measure it in the gas diffusion electrode setup. For the carbon-based gas diffusion layer, we take out of the vacuum filtration a circle of 3 mm and place this inside a hole of a larger substrate. On top we place a nephine membrane and press this at room temperature. On the other hand, for the titanium felt, this regular procedure we are using was not possible. So instead I had to perform a simple hot pressing here at 135 degrees because otherwise I only had poor electric connection reaching high resistances of several hundred of ohms. After talking about the preparation of the catalyst films and the electrodes with the two substrates, I now want to talk about the results that I obtained at 60 degrees. And when we look at the tafel plots of both activity measurements, we see really comparable results. And therefore we can conclude, yes, also the titanium felt can be used in the gas diffusion electrode setup. Looking closer at higher current densities, we seem to see some deactivation of the catalyst in the titanium felt, but this is probably only traced back to the peeling off the nephine membrane that I observed at the end of the measurement. Therefore, for measurements at high current densities, professional hot pressing seemed to be necessary. And by that, I hope I could convince you that the gas diffusion electrode setup is a straightforward testing device for oxygen evolution reaction catalysts. By showing you that the gas flow rate, as soon as it's high enough, is not mattering in our measurement, that we reach comparable results as compared to the RDE setup, that the carbon gas diffusion layer we are using is stable enough during our performance measurements, and that also the titanium felt is possible to be used and reaching comparable activity results as with the carbon gas diffusion layer. When you are interested in more details about the influence of the gas atmosphere or kinetic studies at different temperatures, please check out my publication in Jack's Gold. And by that, I want to thank Matthias Ahrens and the members of his group who were involved in this project, collaborators from University of Copenhagen and Technical University of Munich, the funding, and the organizers for giving me the opportunity for this talk, and finally you for your attention.